Hello and welcome to video 3.2, all about work. We have already said that energy is the ability to do work. So now we have to look into work in more detail and see what that actually means, and to look at energy and work and their relationship together from a different perspective. Work is done if an applied force moves an object through some distance in a direction parallel to the direction of the force. So if we write this out into an equation, then our equation for work is that work done is equal to a force times distance moved. Now the key here is that the force has to be parallel to the distance that's moved. If it's not, then there will be no work done. Force we know is measured in newtons. Distance moved we will measure in meters. So work done is measured in Newton meters. But work is also, as we said, energy. They are the same thing because energy is the ability to do work. So even though based on this, the units for work are Newton meters, they are also joules. If there is no motion, there is no work. If there is motion but not in the direction of the force, then there is no work. Even though it may feel like you're doing work, there is no work. So, for example, if we have our person who is standing there and they are holding a box. It's a pretty heavy box by the looks of it. So this person is holding a box. If there is no motion, there is no work. What if the same person is holding this box, but now they're moving forward? In this situation, we need to look at what is the force that they're applying to the box and what direction is it in. Well, the force that they're applying to the box is an upward force that fights against the downward force of gravity. So the force in this case is a vertical force. The motion, however, is a horizontal force. The force is not parallel to the distance moved, so again, the work is still zero because the force is perpendicular to motion, not parallel. What about if the person gets tired and they've gotten to wherever it is they're taking this box? Let's say that they're going to put it on this little table. So now they're going to lower the box down. Well, now in this case, remember that the force is they're applying an upward force to keep it from falling. And the motion, since they're putting it down on the table, is downward. Because the force and the motion are parallel to each other, then there is work being done, and work is not equal to zero. So when we're talking about work, we have to keep in mind that there has to be an applied force, there has to be motion, but the force and the motion must be parallel to each other. Otherwise, even though our muscles might be doing work, and we could look on the muscular level or the cellular level and say, yes, we're doing work, in physics, when we look at the whole system, we would not be doing any work. Let's look at an example of pushing a box. Okay, let's say that we have a surface, and on that surface we have a box which happens to have a mass of 20 kilograms. Let's say that we apply a push force to the box and it moves a distance of 5 meters. The question is, how much work is done? Well, we also have to know a couple of other things. First of all, let's assume that the surface is free of friction. When we are doing this sort of problem, the other things we need to look at are making sure that there's no other forces acting on it other than the push force. In this case, we also have the force of gravity And because it's on a surface, we have a normal force. But neither the force of gravity nor the normal force are in the parallel direction to the distance. So they don't count in terms of work. But it's always a good idea to check to make sure that you don't have any other forces acting on the object. So let's see. Let's say that the push force is 100 newtons. Then the question is, how much work is done? Well, work is force times distance, so 100 newtons times 5 meters. So we apply 500 joules of work to move this box. If we're applying 500 joules of work to the box and the box is moving, then that means that the work done is really an energy transfer. If this is true, then that means that this work that we're putting into the box must be converted to some sort of energy. Well, the box is moving, so that means that the energy, the work rather, goes into kinetic energy. So let's use that to figure it out. Since there's no friction, we don't have to worry about losing any of our work into anything else but kinetic energy. So that would mean that if work becomes kinetic energy, then work must become 1/2 mv squared. And we can then use this to find out how fast the box is moving at the end of the 5 meters. So 500 is 1/2 times 20 v squared. So 50 is equal to v squared, and v then is 7.07 meters per second. So, simple problem, box moving across a frictionless surface. We require 500 joules of work to get it to move 5 meters, and that gives it a final speed of 7.07 meters per second. If there's friction, it gets a little bit more complicated, and we'll come back to that later. But the key here is to remember that we are only looking for parallel forces, forces that are parallel to the direction of motion. Let's do something a little bit different. Let's look at if we are lifting a box. So let's say that we have a box. Let's say that our box has a mass, in this case, of 10 kilograms. We know that it has a weight due to gravity going down. We're in the process of lifting it. We've already taken it off of the ground, so we don't have a normal force to worry about. But we are applying a force upward that we will call lift. Okay, and let's say that we want to move the box up 2 meters to get it to a shelf that it needs to be stored on. If we are moving this at a constant speed, then the weight of gravity, the weight due to gravity rather, and the lift force should be the same because it's not accelerating. Well, if that's the case, then our lift force will be equal to 10 times 9.8, which is 98 newtons. The work done is 98 times 2, which is 196 joules. This 196 joules worth of work is work that we had to put into the box to get it to go up. What if we get it up 2 meters and stop moving for a minute? Then what happens? Where did that energy of 196 joules go to? Well, we could think about it as going to potential energy of the box, since it is now 2 meters above the ground. However, the other way we need to look at it is we are doing work on the box, but at the same time, gravity is also acting on the box, and gravity is working against us. So while we're adding 196 joules of energy into this box as work to get it to move up, gravity is really pulling that 196 joules of energy out, trying to pull it back down again. So the end result is that the total change of energy in the box is actually 0. because our work in has been being canceled by gravity's work out. So when we stop it up here at the 2 meter mark, it's not going to have any kinetic energy, so our energy in isn't going to be going to kinetic energy anymore. It can't just disappear. But if we think about it as it goes back into the ground because gravity is pulling against it, we're still conserving energy as we should. Let's look at a situation that's a little bit more complicated than either of these two. If we have a situation where there is more than one force acting on an object, causing it to move in a direction that is parallel to the force, then we can no longer just think about work being force times distance. Instead, we have to look at net work, or we have to look at the sum of the works. So the sum of the works, or the net work, would be the amount of work from force 1 plus the amount of work from force 2, etc., till you get to the amount of work from all of your forces that you have going. Keeping in mind that all of these forces are all working parallel to each other and to the distance of travel, we can rewrite this as F1d plus F2d plus etc., plus Fnd. So then if we pull a d out of everything, what we really end up with is that the net work on a system or on an object is the net force times the distance. Well, that's beneficial to know, because then that means that if we can figure out the net force on an object, then we can calculate the net work without having to do individual works and then add them all up at the end. This idea of net work being related to the net force and the distance, along with what we had said before about where does the work go and what does that amount of joules go to and it becoming energy, is called the work-energy theorem. And the work-energy theorem basically means that the net work on a system is equal to the change in energy on the system. Typically, that's going to be kinetic energy. That's how we're going to see it, but it doesn't always have to be kinetic energy. It could be in other terms like in temperature or in heat or things like that. But we're going to assume that it's going to go to kinetic energy the vast majority of the time. So I can put a little k here. So again, net work is net force times distance, and the work-energy theorem tells us that work and energy are basically the same thing. If you put a certain amount of work into a system, then that means that work has changed into a certain amount of energy within the system. So let's do a problem where we're required to find the net work and see what that does and how we can use the work-energy theorem to come up with speeds. For our problem, let's go back to our box again, our original box of 20 kilograms. We're still going to push on it with 100 newtons. We still move it 5 meters, but now the surface is no longer frictionless. There is now a force of friction that is 80 newtons. There is still gravitational force, there is still normal force. Those are still irrelevant to the work that we are doing on the box and against friction. But now we have to look at the fact that we need a net work. And keeping in mind that net work is the work from the force of the push plus the work from the force of friction, we can either solve this by doing force of the push times the distance plus the force of friction times the distance, or we can solve this using the net force, net force times the distance. It does not matter. We get the same thing. Keeping in mind that forces are in opposite directions, they are vectors, therefore they have to be added correctly with signs. So if we do the net force way, then we have 100 newtons minus 80 newtons times our distance of 5. 20 times 5 means that with friction, we will put in 100 joules of work on the box. Our net work will be 100 joules. It doesn't mean that that's all that we're doing, because we have to fight against friction as well. It just means to move the box 5 meters, only 100 joules of our energy is going there. So with this amount of energy, what happens to the speed of the box? So let's figure that out. Well, again, remember that work being energy means that it is 1/2 mv squared. So 100 equals 1/2 times 20 times v squared. V squared is equal to 10. So V is equal to 3.2 meters per second. So with our net work having to be sort of split between friction and the box itself, notice that we're only using 100 joules. We're only giving the box 100 joules of energy, and our final speed is significantly lower than our original speed on this box when we were just pushing it with 100 newtons. Let's look at one last problem that's a little bit more complicated, because now our angles, our forces and our forces and direction of motion are not going to be directly parallel to each other. We'll have to find parallel forces. Let's look at what happens if a force on an object is at an angle. So we've decided that we're too tired kneeling on the ground trying to push this 20-kilogram box across the ground. We still have our force of friction of 80 newtons. We're still going to move it 5 meters, but now we are going to pull it with 100 newtons of force at an angle of 25 degrees. We've attached a rope to it, and we're going to pull it instead because we're tired of pushing it. It will still have gravity, it'll still have a weight, it'll still have a normal force. Those are still not in the direction of motion, so we're still going to ignore them. But now the case becomes remembering that work net is the net force parallel to the direction of motion times the direction of motion. We are no longer going to have the full 100 newtons. Instead, we are only going to be able to use the force of the pull in the x direction to find our work, because that's the part that is parallel to the direction of motion. So the net work will be the net force, which is 100 cosine 25 minus 80, times the distance, so times 5. We solve this and we end up with work being 53.15 joules. 53.15 joules is almost half of what we had last time, when even though we had friction, our force of 100 newtons was exactly parallel to the direction of motion. So if our work continues to go down, then that means that our change in energy will continue to go down, which means that our final speed will continue to go down. So as you add more and more stuff to the situation, oftentimes that stuff ends up working against you. So you'll still apply 100 newtons of force, but only 53.15 joules of that 100 newtons, if we want to think about it that way, is going to go into getting the box from point A to point B, which means it's going to have a lower speed, which means it's going to take you longer to get it there. So with this information about work and net work, or the sum of the work, and forces at an angle and forces with friction, you will be able to solve the next assignment. So bye for now.